Alright, silly people, here's the situation. The problem asks, is the ground state of the infinite square well an eigenfunction of momentum? Um, and so what I have here is the general equation for a solution for the Hamiltonian of the infinite square well, um, inside the well, of course. And then I've also got the momentum operator right next to it. And for it to be an eigenfunction of the momentum operator, it has to obey this, that the momentum operator acting on the ground state, where n is 1, is equal to some constant value that's not the constant value is not a function of time or space, mind you, times that original eigenfunction, right? So is this the case? Let's see by just doing it. So the momentum operator is minus I h bar. It's times del x, and then that's acting on root 2 over a times sine of pi x over a. The derivative will move right through the root 2 over a. So we do that. We do pick up a factor of just pi over a from the derivative, and then we have cosine of pi x over a. So already this is looking like not the original function we had to begin with, but I'll even try to put it in the form of the original by multiplying by sine divided by sine. So I've got a cosine up top with argument pi x over a, and a sine on bottom, argument pi x over a, with sine pi x over a out here. And now, if we just move the normalization constant over here to live with the sine function and move this stuff back, we see that we have the original function, the root 2 over a times the sine function there, but it's just times this bracketed term. So I'll rewrite it as that bracketed term, I h bar pi over a times cotangent of pi x over a. And then we have the original ground state function, so that's going to be just psi 1 of x. So you can put it in the form of something multiplying the ground state, but the thing that's multiplying it is not a constant. If you look in here, it's dependent on x, so if you try to measure this momentum, the magnitude of it is ranging between whatever pi x over a actually is, and it could be moving left or right because cotangent, it can be a negative value or a positive value, so you really don't have an exact eigenvalue for this. So I would say no, it's not an eigenfunction because you don't get a real eigenvalue. All right.